Hello and welcome to Empowered Learning. This video will be about the process of variation of parameters in solving differential equations, and specifically we're going to use this process to be able to solve non-homogeneous ordinary differential equations of order 2 or higher. So this is the first video in this video series, and what I want to do in this video is take some time to go over the basics of what the variation of parameter steps are, as well as give you a lot of examples. In my second video, I'm actually going to go through how to derive variation of parameters. And so part of the reason that I want to do that is to make sure that you understand why they actually call the process variation of parameters and where the variation in the parameter actually comes from. Okay. One of the things that I'm also going to illuminate here today is why we want to use this process specifically for non-homogeneous ordinary differential equations. And so we can use it for homogeneous equations, or we can use it for non-homogeneous equations that we can solve by doing the method of undetermined coefficients. We can actually use this particular method for that, but it's specifically made for solving non-homogeneous ordinary differential equations where your force function is not one of those that's kind of easy to use with the method of undetermined coefficients. And so that's really the reason why this particular process was made. So I'm just going to read from the notes here. I usually don't do this with my videos, but I am going to read verbatim from the notes here for a while, just so that I can kind of set the stage for what it is that we're going to do before we get into our examples. Okay. So in our introduction to learning about how to solve second order linear non-homogeneous ODEs, which is just my abbreviation for ordinary differential equations, and just in case you're not familiar with that terminology, ordinary differential equations is just the equations where we have regular derivatives. PDEs are partial differential equations, where we use the partial differentiation type of notation. And so we're not going to be dealing with those in this video. Okay. So in our introduction to learning about how to solve second order linear homogeneous ODEs, we learn how to solve such equations as long as our force function, which is also called an external force function, and we normally name it G of X, or some people may name it R of X, depending upon what resource you look at. But I'm going to name it G of X here. And whenever G of X is not equal to 0, is either a polynomial, or exponential, a sine, or a cosine function, or a linear combination or a product of any of these types of functions. Okay. So if you're in a differential equations course, you have probably learned how to do that before looking at variation of parameters. So we know that the method of undetermined coefficients was used to make an educated guess about what our particular solution to our non-homogeneous solution would be. And of course, our solution takes on the form of this y equals y sub h, which is your homogeneous solution, plus the particular solution. So we know that with non-homogeneous ordinary differential equations, this is the form of it. And we know for the homogeneous solution, it's just like solving our second order or higher linear ODEs by letting our G of X equal 0. And just going through that whole process, and depending upon whether you have Cauchy-Euler or a regular linear one, you'll have these different cases that you'll have to determine based upon the roots of the characteristic equation. So, however, our method of undetermined coefficients does not work well, or at best is very cumbersome to work with, whenever our force function G of X is outside of this list of functions that I've just mentioned, okay, that work well with the method of undetermined coefficients. So in other words, if you're not dealing with a polynomial, an exponential, a sine, or a cosine function, or linear combinations or products of those types of functions, then it's kind of hard to make an educated guess. Now, when I say polynomial, I'm also wrapping into there constant functions as well as linear functions, quadratic functions, cubic functions, quartic functions, so on and so forth. Anything that could be expressed as a sum of power functions, and of course constants can be that way too, that's all wrapped up into this function type of a polynomial. So it turns out that we have a more general way of solving these non-homogeneous ODEs that will utilize the reduction of order process, okay? But with a few twists and turns that we normally don't see in performing reduction of order on an ODE. And I'm going to use the acronym ROO, or ROO, just for short, because I'm going to be mentioning reduction of order several times during this particular video. Now, what these twists and turns are actually choices where we get to randomly select conditions about our ODE and some of its byproducts in order to make our non-homogeneous ODE follow the principles of what I'm calling a pseudo superposition principle, similar to that of our homogeneous ODE of order 2 and higher. So what I'm getting at here is that whenever we solve homogeneous ODEs, one of the things that we know is that if I have a y sub h, we know that, let me erase this here, and I'm just assuming a second order, I know that I could assume that my solutions are going to look like this, where my y1 and my y sub 2 are going to be functions that create a basis of solutions for my homogeneous equation. Now, the fact that we are able to assume this, knowing that C1 and C2 are constants, that is the thing that basically embodies the superposition principle. So if I have two functions that create a basis of solutions for my ordinary differential equation, then when I say any linear combination of these two functions will also be a solution, that is a byproduct of this whole thing of being able to use superposition. What we know is that whenever we start to talk about non-homogeneous ordinary differential equations here, if you did not learn this, and hopefully you'll pick this up now, that our non-homogeneous ordinary differential equations do not follow superposition in how it is for homogeneous equations, okay? And to be specific, we know that our homogeneous equation actually ends up being the difference in between two different particular solutions to a differential equation if we're talking about a non-homogeneous, okay? And so we're going to see this fact again, but it's the fact that your non-homogeneous equation is actually the difference in between two particular, your non-homogeneous solution is actually the difference in between two particular solutions to a non-homogeneous ordinary differential equation. It's for that reason that it can't follow superposition like this. And so this is why what I'm calling this is going to be pseudo superposition. And again, we'll see what that's actually going to look like here a little bit later when we come up with a way to be able to interpret what our solutions for these types of equations should look like. Okay. Now, again, I'm not going to go into super detail on this in this particular video because I want to save that for the part 2. For those of you that aren't necessarily interested in, well, how does everything work? You just want to be able to use it. This is the video that you want to watch. If you're more worried about, well, hey, how do I actually derive variation of parameters? Why does all this work the way that it does? Then, of course, you'll need to watch the part 2 video. Now, our primary goal will be to get you familiar with the steps that are involved with doing the process, which is called variation of parameters. And this note here, I've mentioned this before, but I'm going to mention it again. The purpose of variation of parameters method of solving non-homogeneous ODEs of order 2 and higher is to have a systematic way of solving those types of equations when our force function g of x is not equal to 0, and it is not a polynomial, an exponential, a sine function, or a cosine function, as well as any linear combination or product of any of these types of functions. So to clarify what I mean, let's say if I had a polynomial x squared plus 1, and I had, let's say, a sine function, let's say sine of 2x, and let's say I know that my g of x could actually be the product of these two, okay? So if my g of x was the product of these two in my ordinary differential equation, I would not be able to use I would be able to use methods of undetermined coefficients for this, okay? However, if my ordinary differential equation had a g of x that was not this, so let's say I had something like natural log of x times x squared plus 1. The fact that natural log of x is not a polynomial, an exponential, a sine function, or a cosine function, I would have to use the method of variation of parameters to be able to solve a non-homogeneous ordinary differential equation. And so that's really what the method that we're going to learn is for. So afterwards, we're going to do several examples to get you familiar with the process of working out these types of problems. Lastly, we will take some time to discuss how and why this process works, and this will be the part 2 video, and it'll explain pretty much why we call variation of parameters in the first place, okay? Now, one last thing I want to get into before we get into the actual steps is why the method of undetermined coefficients is limited to the function type for g of x. So in other words, we know that for solving non-homogeneous ordinary differential equations using method of undetermined coefficients, again, we have to have either a polynomial, exponential, sine, cosine function, or we need to have the sum and or product of any of these types of functions together to be able to use method of undetermined coefficients. Now, the reason why this works is that all of these types of functions here all have a finite number of basis or fundamental functions that can represent the derivative of any of these functions for any order m. And so I said for n, but this probably should be any here. So for any order n. So in other words, if you want to find out the nth derivative of a polynomial, an exponential, a sine function, or a cosine function, then there is a finite number of base functions that would be able to represent that. And so I'm going to switch over here for a second to demonstrate that so that you'll know exactly what I mean. And so after I do that, I'm also going to compare it to functions that don't have this property so that you see the difference and you see why it is that we need this variation of parameters method here. Okay, so what I mean when I say that these functions like polynomial, sine, cosine, and exponentials, they have a finite basis. What I'm basically saying is that if I take successive derivatives of these types of functions, either they are going to reduce down to 0, as in the polynomial case here, or you're going to find that your derivatives are circular, like how it is with sine, or you have a situation where you just have constant multiples of the same function, like with your exponentials here, okay? So you can see with sine, if I was to take successive derivatives of sine, eventually I get to sine again, okay? So if for every fourth derivative I take, I get to sine again. If I did the same thing with cosine, every fourth derivative, I would get back to cosine again. So what that tells me is that my basis of functions is just going to be sine and cosine, meaning that any derivative that I have of sine can be expressed in terms of a function of sine or cosine. Okay, same thing with cosine. If I take the nth derivative, that could be expressed either as a function of sine or cosine. Okay, With our polynomial example here, notice if I keep on taking successive derivatives, I eventually get to 0. And of course, I could have this x raised to the 21st or something like that, okay? Eventually, I would still get down to 0 for the polynomial, okay? For my exponential here, notice that whenever I take the derivative of y, which is equal to 3 times e raised to the 2x, I am using the chain rule here to get all these successive derivatives. But essentially what's happening is that I'm taking my function, which is 3 times e raised to the 2x, and I'm multiplying it by 2 a number of times. And so here, the basis for the derivatives for this particular function here is just itself e raised to the 2x times some constant. And of course, this lets me know what that constant is going to look like compared to the derivative, but the basis function is just e raised to the 2x. So again, the basis function for a sine function or a cosine function is just cosine and sine. The basis for my polynomials is just going to be x raised to the n all the way down to x raised to the 0, which is another way of saying 1. And for my exponentials, it's just going to be the actual base exponential function itself. So for these types of functions, it is easy for us to use the method of undetermined coefficients because it gives you an easy way to characterize any derivative of order n for these types of functions. And because we can write it in a finite way, that is what makes it good for using a method of undetermined coefficients when we have these types of functions being our external force functions for our non-homogeneous ordinary differential equations. So that is what I mean when I come back here and I say that all these functions have a finite number of basis or fundamental functions that can represent the derivative of these functions for any order n. So that's what I mean by that. Now, what I want to do next is show you why other functions don't necessarily follow or have this particular property. All right, so if we want to look at another function, let's take an easy one here. Let's say y is equal to natural log of x, okay? Well, we know that the first derivative of that is just going to be 1 over x, where of course x is greater than 0. And this could also be expressed this way. If we took the second derivative, notice this would be negative x raised to the negative 2, which is the same as saying this. If I took the third derivative, this would be just 2x raised to the negative 3, or 2 times x raised to 3. And if I did the fourth derivative, then I will have negative 6x raised to the 4. And if I kept on going here, then hopefully you're starting to see that as I keep on going, I'm not going to have a way to be able to express the nth order or the nth derivative of natural log of x as just a simple finite basis of functions. So here I'm just going to keep on going. I don't have anything repeating like circular like how I had with the sine or cosine functions. I don't have a constant multiple of the same type of function as I did with the exponentials. And of course, I can't keep on taking successive derivatives of this and eventually get to 0 like the polynomials. So for these types of functions, there is no way for me to be able to express this as a finite number of functions. And in fact, for those of you that have studied power series, this is one of the reasons why we can rewrite natural log in terms of a power series. But that power series is an infinite power series, which means you have an infinite number of terms that we would have to write out to be able to properly express natural log of x correctly. And so the method of undetermined coefficients doesn't work well with these types of functions. All right, so we're finally at the point where we can start talking about the actual steps. I'm going to give these steps for second order linear ODEs, and I break this up into two different ways. One way is what I call the traditional way, and this would be the way where we'll end up solving a system of equations, and we'll use system of equation techniques, primitive ones as well as higher order ones. Just depends upon what you want to do. We'll use that to be able to solve it. The other way is I'm going to call it the formula way. And so, of course, I'm going to give you a formula to use. And so we're going to do examples practicing both ways so that you can see the variations in what's required doing it each way. Again, two different tools to do the same thing. Sometimes it's easier to do it the systems of equations way. Other times it'll be easier for you to do it the formula way. Just kind of depends. Also depends upon how much of linear algebra you're actually familiar with, because we will be borrowing some stuff from that subject to be able to do some of these problems here. Okay, we don't have to have it. It just makes it convenient if you do know those things. All right, so our step one here is we're going to consider our equation star, which is just our second order linear non-homogeneous equation here. And we're assuming that this g here is going to be a function that is not equal to 0. Okay, and we're assuming that a, b, and c are constants. So we also want to assume that our particular solution, our y sub p, is of this form here and is going to be a solution to our equation star. Okay. Now, if you remember, we talked about pseudo superposition here, and notice that my particular solution for this particular function here, not the total solution, because remember the total solution is going to be the homogeneous solution plus the particular. So what this characterizes is specifically the particular portion of this total solution. Okay. So here, this u of x and v of x here are actually functions of x. Okay. And when we use superposition, superposition says that I can have linear combinations of functions that are in a basis. Okay. So whenever we're talking about the homogeneous ones, these are constants. So these functions here have to be constants in order for me to quote that, hey, I know that this particular equation has another solution based upon superposition. Since this u of x and v of x will not be constants, then I can't say that this actually follows superposition. However, the form in which it's in kind of looks sort of like a pseudo superposition if you bend the rule and say, all right, well, it doesn't have to be constants, but let it be a function and let these functions vary. Okay, just like constants vary. And so this starts to get into why we call it variation of parameters. But again, I'm not going to go deep into that until the second video. Okay. Now, the reason why we assume that our solution is going to look this way is because of the fact that we're actually going to be applying reduction of order to this process. So in other words, whenever we derive it, we know that reduction of order says if I know some solution to an ordinary differential equation, y1, then I can assume that that second solution looks something like this, okay? Which is some function u, which we're just going to assume is a function of x, times the known solution here. And so what we're doing here is we're actually using what we know about our homogeneous solution, corresponding homogeneous solution to this particular equation here, which is just basically this, where this is 0, okay? So we're using that to be able to come up with what our particular solution should look like. Now, again, the reason why we're choosing this way to do this is because recall, once again, that a homogeneous solution is really just the difference in between two particular solutions. Okay. So if I was to take this y sub 1 and replace it with the difference in between two particular solutions and take this y sub 2 and do the same thing, what I would actually have is a particular solution that's actually u of x times the difference in between two particular solutions plus v of x times the difference in between two particular solutions again. So all of this looks like particular solutions, okay? Now for what we're doing, again, we only need to worry about the fact that we have it in this form and use it. But I'm speaking to this now so that whenever we get to the derivation video, for those of you that want to look at that, you'll have a better understanding of why this looks the way that it does, okay? So going back here, we have this ordinary differential equation that is non-homogeneous, so our g of x is not equal to 0. We know that our total solution is going to look like this. Our particular solution is going to be of this form here, okay? So our first step is to make sure that we realize all of that, okay? And so to be specific, you want to know what is going to be your A, what is going to be your B, what is going to be your C, what is going to be your function g of x, okay? So we want to know all of that. And we also want to know that our final solution will have to be of this form, okay? So that's what we want to know there. Now, in step 2, here's where we actually start doing the work. And so in step 2, we simply just find out what is going to be our homogeneous solution to this equation here. So we let G be 0 to find the homogeneous solution, and then we state what those answers are, okay? Now, the thing that we need out of that is these two basis functions, meaning what are the two functions that create a fundamental set of solutions for all of the homogeneous solutions based upon initial conditions, okay? So our step 2 is just basically solve for the homogeneous solution. Our step 3 is that now that we know the basis functions for our homogeneous solution to our non-homogeneous differential equation, and we know that u is a function of x, v is a function of x, we need to find the derivative of u and the derivative of v. But we're going to find it using this system of equations here, okay? And so in the part 2 video, this is the part that I'm going to derive, basically explain why from scratch, how we actually get to this point. And so essentially what's happening here is that whenever we do the whole derivation, this ends up being a special expression that we can set to anything that we want. And so out of convenience, we set it equal to 0, okay? And I go through the process in the part 2 video of why that is. But for here, again, all we're concerned about is we need to find a homogeneous solution so that we'll know what y1 and y2 are. And then from here, we use this information, take the derivatives of both of these functions here, plop it into our system of equations, and we solve, okay? And again, we have several ways that we can solve systems of equations. I've listed some here: substitution method, the elimination, or some people call it the addition method, Cramer's rule from linear algebra, or the Gauss-Jordan elimination, or some of you may know it as taking your system, rewriting it as an augmented matrix, and doing row reduced echelon form on it, or the RREF method, okay? Now, just for my personal suggestions here, I would probably do Cramer's rule first if you're familiar with this particular method from linear algebra, or I would do substitution method. Those are the two that I think that are the most efficient to work with for the types of problems that you're probably going to see in your course. You can do the elimination or addition method or the Gauss-Jordan elimination method if you want, but I think these two are not as efficient as the two that I've listed here. And so most of the examples that I'm going to do are either going to employ Cramer's rule or substitution method, okay? If I do it the traditional way. Now, after we found out what our U prime and our V prime is, then we just simply take the antiderivative of those to be able to find out what U and V are. Once we find U and V, remember that our particular solution is just U times first homogeneous solution plus V times second homogeneous solution. And we can combine that along with the fact that our homogeneous solution in general looks like this. We add these two together here to come up with our final solution. Okay, so again, just to recap, our step one, we just recognize that we have a non-homogeneous ordinary differential equation. From there, we make sure that we understand that the form of our particular solution is going to be U times Y1 plus V times Y2. We understand that our total solution is going to be of the form homogeneous solution plus particular solution. And we note that U and V are going to be functions of X. Our step two, we find our homogeneous solution, which looks like this, by letting our G or G of X in our original non-homogeneous equation be 0 just to find these solutions. And then after that, we use this system of equations to be able to find out what U prime and V prime are, okay? And then of course, you could use whatever methods you want, but Cramer's rule or substitution rule is going to be preferred. Take your antiderivative of U prime and V prime, and then just take your homogeneous solution plus particular solution, add them together. And so that is how, those are the steps for that. Now, alternative method will be to use formula. Now, for the second order ODEs, this is what this formula looks like, okay? And again, we can actually arrive at this just by simply doing the traditional way and doing the substitution method. We will naturally get to this, okay? Now, if we do it this way, one of the things that we have to be familiar with is what is a Wronskian matrix. And so what this actually ends up being is just this expression here. But we know from determinants from linear algebra that this expression here can actually be interpreted as a determinant of a matrix where your first column is Y1 and then the first derivative of it, and second column is Y2 times first derivative of that. So that's what these values are here. You will sometimes see this portion here expressed as Wronskian sub 1, and all that is going to be this same matrix here, but the first column is going to be replaced with the right-hand side of the equations from equations from the traditional way. So here, if this 0 and it's G divided by A here, so what we would do is if I wanted to know what Wronskian 1 was, this matrix would actually look like this. And then this would be the Y2 and the Y2 prime, okay? And if I took the determinant of that, it'll end up looking like this. This sometimes is called Wronskian sub 2. And again, it's the same kind of thing. It's just that now we're replacing column 2 with this 0 and G divided by A. So this will look something like this. And you'll have Y1 and Y1 prime here. And if you take the determinant of that, it'll end up looking like that. So that's essentially what this formula is trying to tell you. Now, the reason why I'm going through this here is because if we were going to actually write everything in formula view, and I'm going to skip down to this right now, then this is what it would look like if we were trying to find the solution to an nth order non-homogeneous ordinary differential equation. You notice how I have the Wronskian sub k in there, where k can go from 1 all the way to n, which is going to be the highest derivative that we see. And if I let k be 1, then it's going to look pretty much like what this is if my n is 2, meaning that my highest derivative is of second order. So my matrices are going to look like this. Okay. Now, for the nth order, notice that this is the k equals 1 column, k equals 2 column, and k equals n column for the Wronskian matrix. And here, let's say if my my n is something really big here, then of course my Wronskian 1 would just be this first column here, replaced with all zeros except for the last one, which is g divided by a. Okay. And for Wronskian sub 2, all columns will be the same here, but of course this column will be replaced with this particular column here. And so that's basically how you use the formula. Again, just want you to get familiar with what this looks like in general. As we go through the practice examples, you'll kind of see how all this comes together. Now, this shows what the solution to what this would be if we actually integrated everything out, okay? And what this is trying to show you here is in this form, we haven't necessarily taken into account of the integration constants, okay? Whereas when I write it this way, I'm taking into account of the integration constant that comes from this term here, as well as the integration constant that comes from this term here being multiplied by the y sub 1s and the y sub 2s respectively. So this is showing you explicitly what all those solutions look like. And what we get for the integration constants here times this negative y sub 1x actually ends up helping us to get this particular term here. And same deal here, this particular term, if I was to actually integrate it out and have its integration constant multiplied times y sub 2, that helps us to get this particular term here. And again, the reason why I say help is because sometimes you'll find that we have to combine stuff together from a homogeneous solution as well as a particular to kind of make this work. All right, so I've taken a while to actually go through the whole process of explaining what variation of parameters is and kind of giving you some of the details. But now let's go ahead and start working some examples here so that you can see how this actually works. All right, so this is our first example. We want to solve this non-homogeneous equation here that just so happens to be a second order linear non-homogeneous equation the traditional way, meaning that we're going to use a system of equations here, okay? And I'm asking you to use Cramer's rule to solve for u prime and v prime. So the first thing that we want to do here is make sure that we identify everything that we need or everything that we have here. Now, in the later examples, I'm not going to do this step, but I'm taking my time to do it now so that you kind of recognize where everything is, so that whenever we do this stuff later, you'll just kind of know, hey, this is where that came from. So, of course, this equation here is modeling a times y double prime plus b y prime plus c y equals 0. Sorry, g. And so here this lets me know that my a is 1, my b is negative 2, my c is 1, and my function g, which is going to be a function of x, is just going to be e raised to the x over x. or you could rewrite it this way if you want. So now that we have that, then our step 2 is that we need to find what our homogeneous solution is going to be. Okay. Now note that our homogeneous solution's got to be of the form C1. I didn't write correctly here. So it's got to be C1 Y1 plus C2 Y2. Okay. And we know that if we're going to look at the corresponding homogeneous equation for this, then it's going to look this way. And of course, we have a characteristic equation of r squared minus 2r plus 1 equals 0. And if we factor the left side, that's just going to end up being r minus 1 squared, which is equal to 0, which implies that r minus 1 is 0, which means that r is just equal to 1. So in the language of second order linear homogeneous equations, this is a case 2 situation here. So what this means is that our homogeneous solution is just going to be, let's try to get that together here. Our basis functions are going to be e raised to the x and x times e raised to the x. So solutions will look like this for the homogeneous part. And here, these two functions will create the basis. Okay, so this will be our y1, this will be our y2. So now that we have that together, the next thing that we want to do is go ahead and solve that system of equations. So our step 3, so we're going to solve system of equations below. Okay. And here, our system of equations, this will be u prime y1 plus v prime y2 is equal to 0. And then we have u prime y sub 1 prime plus v prime y sub 2 prime, and that's going to equal g divided by a. Okay. So if we set this up, u prime, and I'm going to go ahead and write this for u prime and v prime, because this will let us know what it is that we're trying to solve for here. Now, since we know y sub 1 and y sub 2, we know what the derivatives are as well. Okay. So we have u prime, our y sub 1 is just going to be e to the x, plus v prime, another thing that we need to solve for, times y sub 2, which is x e raised to the x. U prime here, derivative of e to the x is just e to the x. And v prime here, the derivative of x times e raised to the x, we use the product rule for that. And that'll be e raised to the x plus x times e raised to the x. And of course, the top equation here is equal to 0. So from here, we'll actually take this information and we'll solve for u prime and v prime. Now, using Cramer's rule tells us that we are going to have some Wronskian matrix, which is going to be on bottom. We talked about that before. It's just going to be y1, y1 prime in the first column, y2, y2 prime in the second column. And then for the matrix or determinant matrix in the numerator, we're going to take, since u prime is in the first term here, we're going to take this 0 and g of a, and we're going to plug it into the, you're going to plug it into this first column here. And by the way, let's go ahead and figure this out because I forgot to do this part. Our g divided by a, if you remember, our a is 1, and our g is just this e to the x divided by x, okay? So here, our g divided by a, I'm just going to keep this as e raised to the x divided by x. So this g of a that I have here is literally just going to be e to the x divided by x. And of course here, this will be the y2 prime. And I'll fill all that other stuff in later. So now we have our system of equations here. I'm just going to solve this. This is 0 e to the x divided by x. Our y2, that was x e raised to the x. And here I'm just going to simplify this, factor out, and rewrite it this way to make life a little bit easier. And down here, we're just going to write in what we know. So we got e to the x here, e to the x again, because the derivative of e to the x is just itself. And here we have x e raised to the x over e, yeah, let's erase all that. And here for the second one, it'll be, we said e to the x. Let's get this writing again. Sometimes this thing gets stuck. So we have e raised to the x, x plus 1. All right, and so here we just take the determinant, and of course to do that, this will be 0 times e to the x times x plus 1, and that's just going to be 0 minus, so these two minus the product of these two. So if I multiply e raised to the x divided by x times e raised to the x, these two x's reduce to 1, and I just have e to the x times itself, which ends up being e to the 2x. In the denominator here, I will have e to the x times x plus 1, which I'll just rewrite as e to the 2x times x plus 1, minus, then I'll multiply e to the x times x e to the x, so that'll be just x e to the 2x. Okay. And so now all I need to do is simplify this. So here I have a minus e to the 2x, and this will be e to the 2x here, and I'll have x plus 1 minus 1. And of course, if I do all the math of this, the 1 minus the 1 cancel the 0. The e raised to the 2x here, these two end up reducing to 1. So what I end up with here, oh, sorry, that's not right. So yeah, I skipped the term. So this should be x plus 1 minus x. So yeah, that's what that should be. All right, so I went ahead and got that fixed here. So we have x minus x ends up just giving us 1 in here. And of course, the e raised to the 2x divided by the e raised to the 2x here. All of that will end up just simply simplifying to a -1. So our u prime here ends up just being -1. Now we'll do the same thing for our v prime to figure out what that's going to be. So for the v prime, of course, the setup for the denominator is the same. And since we already know what that is, we don't have to do the whole computation for that again. So for the numerator, we'll have y1 and y1 prime in the first column, and then we'll have 0 and then g divided by a, which is just e raised to the x divided by x for the second column. So in the denominator here, we know that this just ends up being e raised to the 2x at the end of the day, because this x and that x cancels to 0. 1 times e to the 2x is just that. And then we'll just do the determinant for here. And our y sub 1 is e to the x again. Derivative of that is the same. Have 0 e to the x divided by x. We do the determinant, and we end up getting e raised to the 2x divided by x minus 0, because this times this minus that times that. All that over e raised to the 2x. And we see, and of course, we can just get rid of this minus 0 here. So we get rid of that. Then, of course, what that reduces to is just 1 divided by x. So we see here that our v prime ends up being this. So once we have what u prime and v prime are, all we have to do is find the antiderivative of both. Okay. So here our u is just going to be the antiderivative of u prime dx. V is just going to be the antiderivative of v dx. And when we do this, what we're really concerned about is just the root function here. Because one of the things I want you to recall is that when we set up our solution here, so when we're at this step 3, remember that our goal is to find out this total solution here. Okay. And so in knowing that, we know that the y sub p part actually looks like this. Okay. So my point in saying all of that is we know what the homogeneous solution already looks like. So that part's taken care of. A particular solution, by definition, is a solution that doesn't have any arbitrary constants in it. So here we don't need we don't need arbitrary constants with the u and the v. Okay, so we just need specifically what the root function is. And remember, this actually comes from the whole reduction of order thing that I talked about earlier. Okay. All right. So in doing this, we know that the antiderivative of -1 dx is just going to be minus x plus some constant there. The antiderivative of 1 over x dx is just going to be natural log of absolute value of x plus some constant there. And we simply say that u is going to be minus x and v is going to be natural log of x, just to make life simple for ourselves. Okay. All right, so now that we have this, we know that our solution y sub p, which is u y1 plus v y2. that ends up just being minus x times y1, which was e raised to the x, plus v, which is natural log of absolute value of x, times y2, which was x e raised to the x. And so because of that, we know that our total solution, which is the sum of the homogeneous plus the particular, is going to be c1 e raised to the x plus c2 x e raised to the x. And remember, that comes from our homogeneous solution part, plus, or I should say minus, since this first term here is negative, I'll go ahead and write it as negative here. So let's say minus x e raised to the x plus natural log of x times x e raised to the x. And so now what we want to do is condense this down some. Okay. So to do this, we see that we have these three terms here that have x e raised to the x in it, but since this third one has a natural log of x times it, we're just going to leave that one alone. So we'll say c1 e raised to the x plus, we'll say c2 minus, let's say 1 here, times x e raised to the x plus natural log of x times x e raised to the x. Okay, so that's actually what it ends up looking like. What you could do to simplify this even further here is we could just say, well, let's let this c1 be a k1, and let this c2 minus 1 here be a k2. And we'll just specify that at the end. So here we'll just allow this to be a k2, where c1, or k1 is c1. I'll write it like this. And our k2 is c2 minus 1. And so this is what our actual solution would be to this particular non-homogeneous equation. So this is the process that we go through if we do it the traditional way, and of course using Cramer's rule to be able to solve for our u prime and our v prime. This is what an example of that would look like. All right, so for our next example, we're actually going to solve this second order linear non-homogeneous equation using the formula way that I mentioned earlier in this video. And so we know for second order linear ODEs that are non-homogeneous, there is a specific formula that we use. Okay, and so I'll go ahead and just write it here. And this is for the actually, I could use it for the entire solution. But in this example, I'm actually going to use it for just a particular solution. And I'm going to do it that way since we're actually going to solve for our homogeneous solution first. Okay. So I'm going to sort of augment this a bit here. So I'm going to write the entire formula first and then explain how I'm going to shorten up the process here. So this is the actual formula that I'm writing, and this will give us the entire solution on its own without any extra details. Again, I'm just writing this down so you have reference to it. So this would be the actual form that we would use here. And in integrating this, evaluating this integral here, we would have an integration constant, and that integration constant would spit out the actual portion that would be our homogeneous solution here, okay? However, what I'm going to do is I'm going to rewrite this. I'm just going to say same as y, but don't write out integration constant. Okay. And so again, I'm doing that because I'm leveraging the fact that we could actually look at this equation here and figure out what its corresponding homogeneous solutions are, and easily use that, and it'll make the computation be a bit more simple. Okay. All right. So here we want to find out what our homogeneous solution will be. And again, we want to do that because we know that our total solution is just going to be a sum of the homogeneous and the particular solution here. Okay, so we're going to find this first. So here that means we have to solve this particular equation. And we know to do this, we need the characteristic equation, which is going to be r squared plus 1, which is 0, which is going to be r squared, which is minus 1, which by definition, r is going to be plus or minus I, or plus or minus square root of negative 1. And we know that that's the definition for I, or that imaginary number. So this is a case 3, second order linear homogeneous situation. So because of that, we know that our homogeneous solution is going to be of this form, and I'll just write it this way, where our lambda here is going to be 0 and our omega is going to be 1. So this will be e raised to the lambda x times c1 cosine omega x plus c2 sine omega x. I want to make sure that I'm actually using the right variable. Yeah. And so from here, we know that our homogeneous solution, since lambda is just going to be 0, e raised to 0 is just 1. So I just won't write that part. And so we'll just say this is c1 cosine of x plus c2 sine of x. Okay. So this will be our homogeneous portion of our total solution. So now what we're going to do is find out what our y p is going to be. And for here, we know that y of p is going to have to end up being in a form that looks something like this. It's going to be that, you know, u y1 y sub 1 plus v y sub 2. But since we already have this formula up here that we're going to use, we're just going to use it directly. Okay, so we're going to use that directly. And remember that since we already have a homogeneous solution here, I don't have to write out my integration constants whenever I evaluate these two integrals right here. Okay, so I'm going to go ahead and erase this part here and just utilize the formula as is. Okay. Now, in utilizing this formula, I have to identify what y sub 1 is, y sub 2 is, which we already know. It's cosine and sine, respectively. But we also need to figure out what our g divided by a is. And of course, this function here would end up being my g, the cotangent. That's going to end up being my g. This will be a. My b, I don't have a y prime term, so b is going to be 0. And of course, c would be an understood 1. So here I have basically cotangent of x divided by 1. So I know that my g of a in this case is going to be cotangent of x. Okay, so we need to identify what that is, as well as the y sub 1, y sub 2, as well as what our Wronskian expression will be. Okay, so we're going to specifically identify these and then use it in the formula. So my y sub 1 is cosine of x. Y sub 2 is sine of x. My g divided by a is going to be cotangent of x. And then we'll go ahead and calculate what our Wronskian expression will be. And I'm doing this just to kind of remind you the connection in between this expression and a determinant. That this is just going to be y1, y2 prime multiplied together minus y1 prime, y2. Okay. And so this means that I would have to know what the derivative of y sub 2, which in this case is going to be cosine, and derivative of y sub 1, which is going to be minus sine. So if we write this out, y sub 1 is going to be cosine of x. y2 prime is going to be another cosine of x. So this will be cosine squared minus y sub 1 prime. That's going to be a minus sine x. And y2 is going to be another sine x. So subtract the negative, same as addition. These two together work to be sine squared x. And of course, we know that this is fundamental identity here. Cosine squared plus sine squared is equal to 1. So we know what our Wronskian expression is going to look like. So now from here, we'll just use the formula to find our y sub p. And again, remember, the formula that we're going to use actually gives us the entire solution if we write out the integration constants. If we don't write out the integration constants, then it only gives us the particular solution y sub p. And since I already have the homogeneous solution, I'm not going to write out the integration constants because that's what it's going to end up looking like if I did. Okay. All right. So let's write out the formula again. And I'm going to skip writing the of x part to it. So we'll just say all this business here. I'll write this part. And then plus y sub 2 integral of y sub 1 times g divided by a over Wronskian expression x. And so now we'll fill in all our information. So y sub 1 is cosine. Wronskian here, all this is just 1. Y sub 2 is going to be sine of x times cotangent x dx plus y2 is going to be sine of x times integral of y sub 1, which is cosine of x times cotangent x dx. And of course, from here, we know that cosine is the same, sorry, cotangent is the same as cosine x over sine x. So this first term here is simply just going to simplify to negative cosine of x times the integral of cosine x dx. The second term we'll have sine of x times integral of, again, this is cosine x over sine x. And so this ends up being cosine squared over sine. Okay. Now with cosine squared, to get this into a form that's going to be a little bit more malleable for us to use, we want to remember that cosine squared is the same as 1 minus sine squared. So I'm going to erase this cosine squared part here, and I'm going to rewrite it as 1 minus sine squared. Okay. Now, with us having 1 over sine squared, we could break this up as 1 over sine minus sine squared over sine. And what that will end up being is cosecant x minus sine x. Okay. So I'm going to erase this part here and rewrite this 1 minus sine squared x divided by sine x as cosecant x minus sine x. And so in that form, we'll have it in a form to where we can easily integrate this, provided that we remember what these antiderivatives are. So here, let's go ahead and put this in. Okay, so now that we have that, then the rest of this will be relatively straightforward. So all we have to do is evaluate our integrals. And remember that in this example, I'm not going to list out or write the integration constants because I already have those, what that's going to end up being here in my homogeneous solution. Okay. So here, y sub p. We know that the antiderivative of cosine is sine. And again, we're not going to write out the integration constants. Have sine of x here. And of course, if we take the antiderivative of cosecant, the antiderivative of cosecant will be natural log of absolute value of cosecant minus cotangent. That's one of those ones from your second year calculus course that you may have forgotten. But you can derive this in a couple of different ways. The antiderivative of minus sine is going to be a plus or positive cosine. Okay. And so from here, all we have to do is just simplify as much as we can. And the main thing here is to distribute this sine x to both terms. Okay, so once we're here, we see that this first term and this last term end up canceling to 0. And what we have left is just the sine x times natural log of the difference in between cosecant and cotangent, all that in absolute value bars there. And that is our particular solution. So now, finally, what we do is we find y, which is equal to homogeneous solution plus particular solution. Okay. So if we remember here, our homogeneous solution was just C1 cosine of x plus C2 sine of x. So we're just going to take that and add this together here. So we have C1 cosine of x plus C2 sine of x. And then we're going to add on our particular solution, which is sine of x times natural log of cosecant x minus natural log of absolute value of cosecant x minus cotangent x. And so this ends up being our actual particular solution to our non-homogeneous equation.